Am I audible?
Sir, your voice is low, bit low.
Am I audible? How the course is going on? Good. Course is good now. Hello. Am I audible or? Okay. Today actually we will solve that problem sessions in the assignment number 8, and you people have some doubts, so then we can clarify in detail. Okay. And tomorrow, yeah, tomorrow session actually we'll look for the others. How the mm, new weeks actually, they are actually asking for this MATLAB and Python. Some practical works regarding MATLAB and Python is there, no? The new weeks means, yeah, the one which we are going to discuss tomorrow. Yes, okay, yeah. Join my. But I will look these assignments, and if you have some older doubts and other things, actually we can check for that one also. Okay. So this is the first question. The axial distance from the beam center to the plane at which the beam diameter increases by a factor of dash provides the Rayleigh range. Okay. Okay. Oh, okay. Oh, sorry. I didn't share the screen. So, now you people can see the screen now. Okay. Yeah. This is our first question. The axial distance from the beam center to the plane at which the beam diameter increases by a factor of dash provides the Rayleigh range. So let us see what is the question. So we have a Gaussian beam, and it will have a axial direction also. We draw the axial direction. It is something like this way. This is the z axis. And it will have a beam based at the point z is equal to 0. And we already defined that there is a Rayleigh range at some z0 distance. This distance is called a Rayleigh range. Okay. Now, what is the question actually? The question is like that way. Rayleigh range is defined as the beam base changes from this side to this omega z. The question they came in such a way that we are saying that z is changing from 0 to z naught. Now we want to know that omega will change. Omega z will change from omega naught to how much? This is the question. Okay. So you can directly go for that answer. We know the equation for the Rayleigh range. What is the equation for beam radius? Omega naught is equal to omega z is equal to omega naught into 1 plus z by z naught the whole square raised to half. Okay. People are hearing now? Okay. Now the question is like that way. We know that we moved from z to z naught. So omega naught into 1 plus this z will become z naught. Z naught by z naught the whole square raised to half. So it will become omega naught into 1 plus 1 square raised to half. This will be 2. So omega naught into root 2. Okay. So looking the answer. Actually, they are given in such a way that they we can say that Rayleigh range can be defined as when we are at the Rayleigh range, the beam radius will be root 2 times beam based. So the answer will be root 2. Okay. Next. The base diameter of an optical beam is same as that of a Gaussian beam. Then the m square factor is the ratio of the. This is a direct question. So this is like that way they are asking what is mean by m square factor. What is actually m square factor? So we can say that actually you have a laser. I can say that I have a laser which is a original commercially available practical laser. I'm saying I'm having a laser. So it will have a window. It will have a laser window and it will have a particular laser aperture. This portion from where this beam is emitting, that is called a laser aperture. And it will be more or like a Gaussian beam. So I can practically calculate the radius of the beam, and actually these are characterized by different parameter. Na? The laser can be characterized by, or this beam can be characterized by different parameter. If you are checking, you can see that this beam, you can say that the beam will have a particular beam diameter characterized by the omega naught, and it will have a particular confocal parameter of the radial range characterized by z naught, and the beam is composed of a particular frequency or the wavelength of the light, and that is characterized by its wavelength lambda. So these are actually the parameters which is actually defining the particular laser beam. And in a model system, actually what we are doing, we are actually considering it as a Gaussian beam, and we are doing all the calculation by considering it as a Gaussian beam. So we will have a particular Gaussian beam, and if the same Gaussian beam, the Gaussian beam have a parameter which is actually comparable to this thing, like this omega naught should be the this same Gaussian beam, and this wavelength also should be the same. And if you are calculating a Gaussian beam having, means this is like a laser beam having a definite properties, like it's a practical laser beam having particular properties. So you can actually measure using your instruments, you can actually measure the properties of the beam, and this is actually the Gaussian beam which is having a particular characteristics as an ideal characteristics. So actually we can compare the properties of this Gaussian beam to this practical beam, and how the practical beam is towards this ideal Gaussian beam is given by your m square parameter. In that thing, actually you are calculating the beam divergent angle. So the parameter m square is defined as theta prime divided by theta, where theta prime is the beam divergence angle of this particular practical Gaussian beam. So we can say this is the theta, and this is actually the beam diverging angle of your original Gaussian beam. This actually you can calculate theta prime. This is theta. So this ratio is actually defined as your m square parameter of that particular laser. Okay. So your answer is actually angular divergence. So it's actually the m square parameter is defined as the ratio of the angular divergence of a real laser beam to that of an ideal Gaussian beam. Okay. Now we can go for our third question. Now you can see that two beams of wavelength 450 nanometer and 633 nanometer are focused using a lens. Which of these beams form a smaller focused spot? Okay, people are hearing now, because I cannot see this whether my connection is lost or something or no. I cannot understand. If you are saying yes or no, I can understand. Am I audible now? Lost my connection. Sorry, I lost my connection. Till what time I was here? Whether we could you could see that whether I am solving this problem, second problem. No. Oh, oh, screen is now. Whether you could see I'm solving this problem, second problem. It's a quite right. It's a direct question only. It's actually showing the how the ratio of the beam divergence is actually giving the m square parameter. You're hearing that? Yeah. Is there any doubt regarding this question? Beam parameter ratio. Yeah, this is the beam parameter product. Yeah. One. So it is like a, now you see that now you just think that you have a laser beam. So I'm I am actually focusing a Gaussian beam using a laser, using a lens. Okay. What are the properties will get changed? Just think that I have a Gaussian beam. It's coming. After this one. So actually, this is a particular Gaussian beam. Correct? Then after this one, what happened? Since this is a Gaussian beam, after the focusing also it will be another Gaussian beam. Okay. Yeah. So actually what is happening? Lens is transforming one Gaussian beam to another Gaussian beam. So depending on the nature of the beam as well as the nature of the lens, you will have a different Gaussian beam from one side to another side. So in that case, if you are checking, now you can see that, just think that this is a normal Gaussian beam. A Gaussian beam, I am saying that it's a fat Gaussian beam. So a fat Gaussian beam, actually you can think it as like a normal lens, normal parallel beam. Just think that it's a long, it's a fat Gaussian beam, and think that, and I am using a lens having a very short focal length, means a very high power lens. So what happens in the case of a ray optics? What you will see After this parallel beam is passing, it will go and focus. Okay, this is the ray equivalent of a focusing of a beam by a lens. But now think that if this is not a parallel beam and this is a particular class of beam called Gaussian beam, so what will happen in the case of a Gaussian beam? Whatever the beam which is coming will be Gaussian in nature. So the beam itself has a focusing tendency. So I say that this will be my incoming beam, and I'm using a lens to focus. This is the same kind of lens I am using. So I may get a something kind of a focus phenomenon, but it is not like a exact focus. In the case of ray optics, we can say that focal spot will have a sharp focusing diameter. It will be like a point. Okay, it will be like a exact point such that all rays will pass through that particular point, and the point will not have any dimension. Means it is a very sharp point. Understand? Yeah. In the case of Gaussian beam, what will happen? This is a Gaussian beam which is having a beam diameter of some omega naught, and the beam itself has an inherent divergence. Okay, so it will have a theta divergence. Now after the transformation, what will happen? Because of the properties of the lens as well as the Gaussian beam, this will also form a Gaussian beam. But what kind of Gaussian beam? It will be like a tight Gaussian beam, something like this. Okay, now see what is the difference here. Here in the case of a geometrical optics, we will say that this has a, there is no beam diameter at the focus. It is like everything is passing through exactly at one point. But in the case of Gaussian beam, there will be a finite diameter here itself. Okay, so that is after transformed Gaussian beam having a beam waist of omega naught prime, and you can see that it will have a diverging angle theta prime, I can say. Now you can see what is the difference here. Now you can see that how much tight your focusing is happening. So how much your omega naught is getting decreased, that much your beam divergence is increasing. So here you can see that your omega naught is some more bigger, so corresponding the beam divergence is some more smaller. Now whatever a lens is doing, lens is actually, if it's a high power lens, it's actually tightening your beam by focusing it at a point. But yeah, as it's a Gaussian beam, it cannot focus at a point. It will form another transformed Gaussian which is having a particular beam diameter which is much more smaller compared to your initial Gaussian beam diameter. But what you are going to compensate with that one, if you are tightening your focus spot, similarly you are going to get a diverged Gaussian beam. The Gaussian beam have a inherent divergence is much more higher compared with your the incoming Gaussian beam. So this product is your omega naught, is defined as a omega naught into theta. You can say that theta naught is equal to omega naught prime to theta naught prime. So actually what is happening, the magnification, you can define your magnification as a m is equal to omega naught into omega naught prime divided by omega naught. You can define. So how much it is increasing or decreasing your beam. So similar way, what will happen? Your theta can be go in the other way. If your beam is getting diverged, your theta will get decreased. So theta will be theta prime divided by m. Okay, so or m is equal to theta prime divided by theta naught divided by theta, or theta naught divided by theta naught prime, you can say. So this is actually, there's an inverse relation between this magnification factor. So actually you can directly see like this way, how much tightening is happening by the lens, that much divergence is happening by the lens. So you can define one beam parameter product in such a way that your omega naught into theta naught, these are like a before the beam entering into the lens, so equal to same as omega naught prime to theta naught prime. So these are the product which is coming after the lens, and that ratio is actually, so from here itself you can define the ratio. Just give this theta up this side and other side. So you can define like a theta naught divided by theta naught prime is equal to omega naught prime by omega naught, and this is actually defined as the magnification of your Gaussian beam by that particular lens. Got it? Okay. So this is actually your magnification factor, and the magnification factor is not a simple magnification like your lens. That magnification factor also depends on your focal length, where the position of the lens is, like different parameter, and the confocal parameter of the lens or the beam is different. Okay, that will go now. So this is your second question. So here you can understand now, this is actually the one which you have to see. So the practical application will come here. I will just discuss that when we are discussing the next question. I will discuss that one. Now you can see that in the case of a ray optics, we are saying that focus is a point. Point means it does not have any dimension. So it is like every ray which is coming parallel is passing through a single point. So that point does not have any dimension. But in the case of a Gaussian beam, you can see that it is not a point, it is a disk having a certain width or certain diameter or certain size. Okay, this is the important thing you have to see when we are looking for all the imaging and other things. Okay, now we can go to our third question. Two beams of wavelength 450 nanometer and 633 nanometer are focused using a lens. Which of the beam form a smaller focused spot? This is the other question. The question is like very simple question. For answering, it's very simple, but actually this containing a lot of information. Okay, now see. So this is the thing which we already defined. Now the question is like that. I have a lens and I am using two Gaussian beams having the same parameter. So what are the beams? One is a 450 nanometer and other is 633 nanometer. It's something like a some or 450 like some around some blue region, and 633 some red. So So I have a two Gaussian beams having similar property, but only it is difference in the wavelength of the light. So it is like a one beam of red and another beam of blue. I am focusing. The question is like that way. After getting focused, how will be my focused spot? That was the question. So I'm giving this a representation image like that way. If it's a ray optics, this will be my focus spot. My question is like that way. How will it get focused? Which will have a longer diameter after focusing? That's the question. So we have to see the how the beams are getting focused and how it's getting. So in the case actually we have a direct equation. Okay, so these things are actually discussed in the class. We are having the beam diameter after transformation through a lens. So I can say that 2 omega naught will be my beam diameter. 2 omega naught is defined as 4 by pi into lambda into f divided by 2 omega naught. Okay, so 2 omega naught. 2 omega naught means this will be the beam diameter at this position is defined as a 4 by pi into lambda into f by 2 omega naught. So here what are the parameters which is depends on the wavelength? It's a 4 by pi. 4 is a constant, pi is a constant. F is the focal length of the lens. That's a constant. 2 omega naught. We already said that the incoming beam have the same parameter. So this will be like 2 omega naught. So my question is that one, 2 omega naught prime. What will be my beam radius? So actually you can see that 2 omega naught prime is proportional to lambda, because this this position, this f is a constant, 2 omega naught is a constant, 4 by pi is a constant. So you can say that 2 omega naught is proportional to lambda. Okay, so 2 omega naught is actually your beam diameter. So beam diameter is proportional to lambda. So if lambda is high, the beam diameter will be higher. If lambda is small, your beam diameter will be smaller. Understand? So how will it look like? That's why I'm saying that the question is simple. That you can see that 650 will have a more beam diameter than 450. So if you're drawing this image, the red will have a more diameter. It will be something like this way. And the green will have a, or the blue will have a less diameter. Got it? Now the question is that what is the practical application of this thing? How actually this is important? I said that this is actually, yeah, as a question wise, this is like a very simple question, but this is actually a very high relevance in the case of microscopy and imaging. Can anybody tell? Can anybody tell this one? Yeah, proper. Yeah, yes. Actually, now you see that you are going to use a microscope and you are going to image at a different part of your image. How actually the microscope is doing in the case of just think that you have some confocal microscope and I am having a my cell. I have a my cell like this way, and my cell will have a lot of organelles, like it will have a my nucleus I am having, and I am having some different organelles like endoplasmic reticulum, and I am having different vacuoles and some ribosomes and mitochondria and other things I am having. Okay, now see how I am going to put it see through a microscope. This is like a big cell, and I want to see what I will do. I will focus my laser spot through this microscope lens, and I will try to focus at a different position. So it is like a, the spot will go through like this way, and it will show this spot. And in the case of a confocal microscope, what we will do, we actually will scan all this portion. Okay, and we will make a image corresponding to this one. Understand? So just think that in that case, if I am using a small spot or a big spot, which will be better? Which will be better, small or bigger? Just think that, yeah, now seeing that I have a red wavelength which is something like this much big. So when the beam is here, almost this everything, it will consider it as a one only, because of my beam diameter is much more bigger. It will get only 1 point information from here, and next time my beam will be somewhere here, so it will take almost all information from here. Then my beam will be somewhere here, so it will give information like this way. So like that way, actually I am getting image. This cell is getting image. Okay, so if you want to image precisely the whole portion of the beam, actually what you want, you want a very small spot size such that it can cover all minute portion of the image area, such that you will get a very nice high resolution image. So if you are using a high wavelength light, what will have, always you will have a limitation, an inherent limitation, which is coming because of this spot size. So you want to use some lower spot size and other things, but in that case there is also another limitation is there. Yeah, that's actually there. Now you can see that red blue is much more better than red, you can say, correct now? Because blue give a very low spot size, but the problem with the blue is like that way, red wavelength, the cell will not absorb much, means the energy will not get absorbed by the cell much. That's why usually we will use red. But because of this wavelength, actually we have a limitation in the resolution. So this inherent resolution will always come in the case of we are using this kind of spot using image. And you can say that okay, we can use some ultraviolet which will have a very less spot size. But what is the problem with ultraviolet? Yeah, yeah, let it be. I'm not care about myself, even though ultraviolet has another problem, because our optics now, our optics, this lenses may not, yeah, the lens will not diffract properly this ultraviolet rays. So it will not obey like focusing and other things with that range. So again we have a issue with the lens. So yeah, so actually you can see that this is actually the beam diameter is limiting our resolution, and this beam diameter is proportional to lambda. So if you are decreasing your lambda in a very less manner, what you can do, you can get your spot size very small, and correspondingly you can get a high resolution image if you are going for an imaging. Now you can say this is additional information. Anyway, nobody is going to ask in this course. What is the why you may hear about the electron microscope, scanning electron microscope or transmission electron microscope you may have here. Yeah. What is the good thing about this one? This electron microscope? Yeah, it will give, yeah, very high resolution. How actually they are obtaining very high resolution? Because they will accelerate the electron. And you may have heard about your de Broglie matter wave studies. When electrons are, we are considering it as a particle also. When it is moving with a very fast velocity, we can consider it as a wave. So, but if you are considering it as a wave, the matter wave wavelength of the electron is actually will be proportional to this additional information. You don't worry about it. 1 by square root of v. This v is actually your accelerating potential. So if you are going to accelerate the electron with a very high voltage, you will get a very low lambda. So lambda is inversely proportional to the voltage. So if you are accelerating with a very high voltage, you will get a very small amount of wavelength, and corresponding to that one, you will get a very small amount of spot size. Now another question. This is a addition only. So in that case, whether lens will work? Yeah, yeah. Actually, in the case of electron microscope, the lenses are not this kind of glass lens. Yeah, they will use a, yeah, magnetic lens. There will be a electromagnetic core. Actually, when you are applying current, they will produce a magnetic field, and this magnetic field will interact with this fast moving electrons, which is a charged particle. So they will interact with the movement of this moving electrons, and they will focus like that. So the basic principle will be something like this thing only. But yeah, your lens parameter and other things different, but you will get a very small spot size since you are using a very high voltage. So this is like, yeah, these are the things which we have to understand when we are dealing with these things. Actually, yeah, this is a simple question saying that what is the difference between the two wavelength. So higher wavelength will produce a higher spot size, smaller wavelength will produce a smaller spot size. The thing is that one, yeah, this smaller wavelength means it, smaller spot size means it can give high resolution if you are going using it as for an imaging purpose. Okay. Now, yeah, when a concave mirror is placed at the beam waist of a Gaussian beam, which of the following statement is true about the reflected beam? When a concave mirror is placed at the beam waist of a Gaussian beam. Okay, you can see that how we can place it. Now I have a Gaussian beam. Now it has a beam waist. What is the radius of curvature at the beam waist? At the, for a Gaussian beam, what is the radius of curvature at the beam waist? Any idea? Yeah, I can put it like that. r of z is equal to z into 1 plus z the whole square. Now you said that what is the radius of curvature at z is equal to 0? R, this is z is equal to 0, na? If z is equal to 0, what will happen? Or you can actually change it as z into z plus z naught square by z. Okay? Yeah. At z is equal to 0, r of z will be infinity. Okay? And at z is equal to infinity, what will happen? Yeah. Yeah, again it will behave like a plane wave. So at z is equal to 0 also our Gaussian wave will behave like a plane wave, and at z is equal to infinity also the Gaussian wave will behave like a plane wave, and all the circular nature will be come in from your z is equal to 0 to z is equal to z naught. Okay, you can see that that actually we discussed in the last class. You can see that they will decrease and increase radius of curvature. They will decrease from infinity to a particular value, then again it will increase from that value to infinity in the case of a Gaussian beam. So now come to the question. At z is equal to 0, the Gaussian beam is acting as a plane wave. Okay, so you can actually, yeah, without doing any calculation, actually you can do this answer. Now the question is that at the beam waist we place a concave mirror. At the beam waist we are placing a concave mirror. So the question is that what will happen? Now just think that in the case of a plane wave, if you place a Gaussian mirror, or sorry, a concave mirror, what will happen? In the case of a plane wave, what will happen? Yeah, yeah, it will focus to that. So focus. So now at the beam waist, Gaussian will also act as a plane wave only. So what it will do? It will also focus. Okay, it will also focus the beam, but it will not be like a plane wave focusing. Okay, since it's a Gaussian, it will have a Gaussian character always. So it will focus. That's the first question. So now we have to see what is the original calculated parameter we can see. So when the Gaussian beam is getting transformed by a mirror, we have the equation like that way: 1 by r prime is equal to 1 by r plus 2 by rm. Okay, this is the equation of a Gaussian beam transformed by a mirror. Okay, now you see here. So first question we answered. First question means you understood what is the nature of our beam after reflection. What will happen? You will get it focused. Okay. Now using this equation, we can see some quantitative nature. Now you see that where is actually we kept our mirror at a beam waist. Okay. You're hearing now? So at the beam waist, now you see what is this equation is saying? This equation is saying how a beam is getting transformed after passing through the mirror. This r prime is actually the radius of curvature of the beam just after reflection. R is the radius of curvature of the beam just before reflection, and Rm is the radius of curvature of that particular mirror. Okay, so you can actually substitute 1 by r prime is equal to 1 by r plus 2 by rm. Now we say that this mirror is actually kept at beam waist. At the beam waist, it is equal to 0, r will be equal to infinity. Okay, so 1 by r prime is equal to 1 by infinity plus 2 by r. 1 by infinity is simply this will be 0. So so 1 by r prime is equal to 2 by rm, or you can say that r prime will be equal to rm by 2. Okay, so what they are saying, after the reflection, the radius of curvature of the beam will be rm by 2, where rm is the radius of curvature of the mirror. So the beam radius of the reflected beam will be half of the radius of curvature of the mirror. Okay, you can see the answers. See, so mirror focus the beam to a small spot, and the radius of curvature of the reflected beam will be half of the radius of curvature of the mirror. Okay, so your answer will be this B and C. Now see, in order to generate the smallest possible spot size, which among the following parameters should be selected? Actually, yeah, now so like that way you are going to image some microscopy or something you are using, and you want to get imaged. And we already see that whenever our spot size is becoming minute, we are getting a very good resolution. Okay, now it's your wish to do some studies using like that. So you want a very small spot size, so you will have a laser beam or something you will have, and you want a very small spot size. And what you will do, that's the question. You will have a laser or something. You will have a laser beam, and you want a very small spot size. So what are the parameter you can change? Yeah. So now you see that in order to generate the smallest possible spot size, which among the following parameters should be selected? Now it is a long focal length lens, large beam, short focal length lens, small beam. So now you see that you have a laser system, and you cannot change the laser system, but you want a small spot size. This is the question. So now we already know that what is the, after passing through a lens, we know that our beam diameter 2 omega naught prime will be equal to 4 by pi into lambda into f divided by 2 omega naught. So you can see that this is actually the spot size. This 2 omega naught will be the spot size, and it is actually depend on three parameter. What are the parameter? One is the wavelength of the light lambda, another is the focal length of the lens, another is actually beam waist of the incident beam omega naught. Okay, and these three parameter you have control. Now just think that you have only a particular laser beam or laser. This is your particular laser, so you cannot change your lambda because the wavelength coming out of the laser is a constant, so you cannot change this one. So lambda is a constant, so this thing you cannot change. Now you have only two parameter. What are the things? One is the focal length of the lens, another is your beam waist of the lens. Okay, now you may think that beam waist will be a constant omega naught, correct? You're hearing? Or again I lost my connection. Yeah, I have some problem with my internet, that's it. You are hearing now? No? Okay. So when I lost it, okay, okay. So actually I have three parameter which is defined at my focal spot. One is wavelength, one is focal length of the lens, another is actually beam waist diameter. Now you can see that I cannot change my wavelength because it is a particular laser. You may think that you cannot change your beam waist, correct? But actually you can change. You want, yeah, yeah. What is the thing? Actually what you will do, you can change actually what you want, a very small spotted less spot. So what are the parameter you can change? Focal length as well as omega naught, and this omega naught is may not be the same omega naught which is coming from your laser. What you can do, what people will do is like that way, we will use some lens system we will use, and it will produce a very small focal length. Then it will go for like a very high divergence thing. Then we will use another big laser system such that it will produce a very big, this kind of arrangement we will call beam expander. So what it will do, it will change your small diameter beam to a very large diameter beam. Now you have a very high diameter Gaussian beam. Now that beam, that very big beam, what you will do, that beam you will apply to a lens. Hello. my computer screen. Okay, you can see my screen, but I cannot see my screen. Hello. Oh, yeah. 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 Now it's came. Now it's correct now. You are seeing my screen now. Okay. Okay. Yeah. That the lag was the thing. Yeah. There was. So what we will do? We expand our beam using some beam expanding arrangement. That will be including two lens arrangement, and we will increase the spot size of our beam, and this fat beam we will put to a lens having a very high power. So, we'll have a very high power lens and very small focal length. So what will happen? We will have very small. Okay. So this is actually the fundamental behind it, giving a small process. Maybe some lag in my system. Okay. Now we got the answer. What are the answer? You can use a short focal length lens as well as a large beam diameter. So you have to use a large beam as well as a short focal. But hmm, I didn't get it. Ah, yes. Omega naught will be this one. This is, yeah. So omega naught is actually the one which is before that. So that not to get that much big omega naught, actually we are expanding the beam from the laser. Okay. Now a helium neon of a wavelength of 532 nanometer is producing a Gaussian beam which is having a m square value of 1.1. The beam parameter product is 10 raised to something into 10 raised to minus 7. This is a direct calculation. We have the equation for m square. What is the equation for m square? M square will be equal to pi by lambda in, yeah, pi by lambda into omega into theta equal, or and this omega into theta will be your beam parameter product. Okay, and this m square does not have anything relation with your m. That you should remember. M square is not equal to m square. Okay, that magnification of the m and this m square does not have any relation. Okay, whether I got lost connection. You are seeing this screen, nah? My screen you are seeing.
Yes.
Yeah. So this m square value is defined as pi by lambda into your beam parameter product. So
Sir, what is not equal to what?
Yeah, you have one magnification m,
Yes, sir.
uh, and that magnification square is not equal to the m square value of this thing. Okay, that is a
Okay, yeah, yes, yes.
that's a completely different parameter. Don't think they are some more related. Okay, this is m square value. This is actually defining how a laser beam is related to the original Gaussian image. That one. Okay, so
Yes, sir.
yeah, so we already given that equation. What is a m square is given like a 1.1 is equal to we are having pi by lambda into beam parameter product. So we can get a beam parameter product as a 1.1 into lambda by pi is equal to 1.1 into 532 into 10 raised to minus 9 divided by pi. You get that will be equal to 1.86 into 10 raised to minus 7. You get. Okay, so your corresponding value is 1.86. Okay, so 1.8 to 1.90 you can use. Okay, yeah, here actually based on the following data answer question 8 to 9. This is actually, yeah, 7 to 8 actually. Yeah, this is actually in the order assignment they removed one question. That's why it's happening. Now you can see that a Gaussian beam has a Rayleigh range of 10 centimeter. A converging lens has a focal length of 50 centimeter is placed at a distance of 60 centimeter away from the beam waist location. The beam waist diameter is 1 millimeter. So what is the condition they are having? You are having a Gaussian beam and the beam diameter is given. Beam waist diameter is 1 millimeter. Okay. It's having 1 millimeter and it has a Rayleigh range of 10 centimeter. Here some Rayleigh range of Z naught is equal to 10 centimeter is given, and they kept a lens. They kept a lens at a distance of 60 centimeter. They kept a lens at 60 centimeter, and lens has a focal length of 15 centimeter. Okay, this is the condition. But this is the thing which they given. Now the question is like that way. What is the beam waist diameter of after the lens? So what is the lens will do? Lens will do some focusing. and you will have some beam wave diameter. Correct? This is the initial thing, omega naught, and this will be something omega naught prime. Okay.
Yes.
So what is your equation? Omega naught prime is equal to magnification into omega naught. Okay. This is actually 2 omega naught prime. So you can say that 2 omega naught. So it will be 2 omega naught prime. So it will be same. So 2 omega naught prime is equal to m into 2 omega naught prime. Okay. So first we have to calculate what is our m. Okay. Omega naught is already we know. Omega naught is equal to 0.5 mm or 2 omega naught is equal to 1 mm. This already know. So if you can find out the magnification m, we can directly multiply and get this value. So, but magnification is not a simple parameter. Correct? It has a different components like mr divided by square root of 1 plus r square. Okay, where mr is equal to modulus of f divided by z minus f, and r is equal to z naught divided by z minus f. What is z naught? Z naught is equal to
Pi omega
pi
squared by
omega
lambda.
square
By lambda.
by now. So first what you have to calculate it? First you have to calculate your z naught. So z naught is equal to pi into omega naught square by lambda. So it will be equal to pi into omega. Omega will be 0.5 into 10 raised to minus 3 the whole square by lambda. That's the wavelength. Oh, z naught I directly given na. Sorry. So you don't need to calculate z naught. So since they already given the z naught directly, you can directly
Yes.
put that way. Yeah. So this thing you don't need to calculate. So we can directly go for our magnification. So we have mr is equal to f divided by z minus f. So it will be equal to 50 divided by 60 minus 15, and this will be equal to 0.333, and we have r will be equal to z naught divided by z minus f. So z naught is given as 10, but z minus f is 60 minus 15, that will be equal to 45 and equal to 0.222. Okay, so m is given as mr divided by square root of 1 plus r square. So it will be equal to 0.333 divided by square root of 1 plus 0.222 square. It will be equal to 1.3253. Okay, now you got m. So your 2 omega naught prime will be equal to m into 2 omega naught. So you know that this 2 omega naught is equal to 1 millimeter. So into 0.3253. Yeah, that's the question. Question is not like they are not asking diameter. So they are asking your beam radius only. the beam waist radius they are asking. So you don't want diameter, so you want the radius only. So it will be like omega naught prime only they are asking. It will be like 0.3253 divided by 2. So it will be like 0.162 millimeter. Will get. Okay. So the answer will be, yeah, answer range is like 0.14 to 0.18 millimeter. 0.16 is the answer. So they have checked putting 0.14 to 0.18 as your full answer, full range. Now the next question. Is there any doubt for this one?
No, sir.
No, no. Next, the location of the beam waist after the lens would be dash centimeter away from the lens. Now the question is like that: location of the beam waist after the lens would be dash centimeter away from the lens. So this is the question. They are saying that they want what is the location of the beam waist after the lens. So this is actually defined as your z prime. So you have the equation as the location of your beam waist. So if you have a lens, and lens will have and a particular magnification, and there will be beam waist. This will be another beam waist. This is omega 0, omega 0 prime, and this distance is actually z. This distance is actually z prime, and yeah, in that case actually you have a equation in this kind of thing: z prime minus f is equal to m square into z minus f. Okay, so z prime minus f is equal to m square into z minus f. So this m square is actually not your m square parameter, this is the square of your magnification. Okay, now we have z prime. Z prime is the one which we want. So this z prime will be equal to f plus m square into z minus f. So it is 15 plus m square will be equal to 0.3253 square into z minus f. Z is actually 60 minus f 15. Okay, so the value will come as so calculating the value will come as 19.76 centimeter. Okay, and the answer will be 19.22 19 to 20.50. So around 90.76 is the middle portion. So they put a range as 19.2 to 19.76, 19 to 20.50. They put as a range. Next question. Is there any doubt in this question? Ninth one. Because I have some confusion in that question. Actually, I have doubt in that question. That question I have doubt. Whether you people have any doubt with that ninth question?
So can you explain that again? I got like 5.2 or something.
Ah, yes. This question, na
I
7.1.
got I got 5.2 or something.
Yeah, I think this answer is wrong
Okay.
because yeah, because that question also,
The
because in
solution
the
also
solution
is,
also, yeah,
I didn't understand how we
yes,
were
yeah,
getting that one.
yeah, that I'm thinking. And in that solution also actually they put radius only, they put as that parameter, and the question is they are asking diameter. Even though if you calculate the radius, that we will not get it. And actually we have two equations to get that size of the
Yes, sir.
beam
So
radius, and both is not
can
matching with that one. Yeah, so I have
so can
doubt.
you
Yeah,
yes, can you
yeah,
clarify that?
yeah. I will contact with them, and if they have some clarification, I will ask them to cancel that question.
Okay, sir. Fine.
Yeah, so here actually, yeah. Yeah, here actually I didn't know. Till that, yeah, finding out the Rayleigh range is proper. But after that, yeah, how they arrived at that equation, I have doubt. I think maybe they mistake to say that the location or something they took or something, I have doubt. I then put 1 plus f0 by f whole square, that I have still doubt. And even in that case, actually, they put the beam radius as their parameter other than beam diameter. And they are asking for some beam diameter. Yeah.
Yes.
So this most probably, yeah, I will clarify with them, and if the question is wrong, I will ask them to put the zero credit for that particular
Yes, sir.
question. So, and how other things are going on? It's good. Other courses means how the
Uh,
new,
the new content, yes, sir.
yeah.
The week 9 where uh, it was, I think Python was being taught, sir. There, I think they were using Python 2.
Okay,
So I only knew how to use like Python 3, so it
but
was a bit of
actually
trouble.
it is like optional kind of thing, nah?
Huh,
Because
yes, sir. Huh.
yeah, because
I had, huh. I
yeah.
saw like which and all was like how you can convert it to like Python 3 or something.
Okay, because
This,
I am actually much more familiar with the MATLAB, so I may be doing
okay.
all the
Huh.
things with the MATLAB. But yeah, I will
Okay.
check how the Python code is running. That I
Yes,
will
sir.
check.
So like I even put in the feedback form. So like if
Yeah.
they can provide us with some sort of Jupyter notebook or something,
Okay. Okay.
where with all the Python 3 code and
Yeah.
the Python 2 code,
Yeah.
it'll be helpful because the lectures which are being taught is on Python 2, sir.
Yeah.
Python 2 very less people use.
Yes. Yes. Yeah. So whether you could convert that basic things to Python
Ah, I
3?
converted. I
Yeah.
converted, sir, and I can
Okay.
share
Okay.
the notebook which I
Yeah, yeah,
provided.
yeah, 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 yeah. That you can do, because that time actually we had option, like we can
Yes,
do
sir.
either MATLAB or Python. Because since I
Yes,
was
sir.
familiar with the MATLAB, I was using MATLAB only.
Yes, sir. Yes.
But yeah, because actually there is no limitation, like if you can do whatever there, like that basic part, you can directly put either in Python
Yes,
or
yes.
MATLAB or whatever you
Basically,
want to
like
do.
they use
Yeah.
this thing called PyLab or something, sir. And I
Okay.
use
Okay.
Matplotlib PyLab.
Okay. Okay.
So
Yeah.
like that difference is it.
Yeah. Yeah. Anyway, that will not going to be any issue. So
Yes, sir.
yeah,
This
what?
like just this codes and all any codes if they can just
Yes, 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 yeah.
send like a link or that will be like very useful.
Okay, okay. I will check that out with them. Because
Yes.
yeah, whatever I am using, I may be using MATLAB. So yeah,
Yes, sir.
don't.
Even in MATLAB, like a live script option, script if you can share with us, it will be like.
Yes, yes, yes. Because of whatever I am coding, what that I will show and
Yes,
share
sir.
that. Yeah. Because yeah,
Yes.
that's the thing I am saying, that I may be using MATLAB, but it is not
Fine,
like
sir.
a,
No problem, sir.
yeah, limit for
Anything, any
yeah,
language is fine, sir.
yeah, yes, yes.
Thank
So
you, sir.
if you people can see and do whatever you want to use, actually it
Yes,
is
sir.
fine, no problem with it.
Yes,
Because
yes.
some people may be using some another language, or if you
Mm-hmm.
can do something, actually it is like you have to understand the concept, how it is really coming. Actually they will give
And
a,
then we have to code it. Yes.
yeah, that's the thing. Yeah, that's all. People have any doubt for this session?
Uh, that's all I had from myself. Like this Python card, this thing was a bit
Yes, yes,
problematic. So
yeah, that will